Hello, everybody. Good evening. I see two chats there. Good evening, Hamsini. Good evening, Shailaja. I hope everybody is
Good
doing
evening,
good.
sir.
Good evening.
Good evening,
Yes. Good evening. So we have 10. That means excluding myself and Nessin, I have 8. Maybe wait for maybe 2 more minutes. Let our friend join. And then we'll start. People, and I just wanted to tell one thing. See, sometimes what to say, like mostly what will happen is we will be going a little slow, and your school would have completed that particular chapter or whatever be the chapter it is. Okay, so if at all you feel that I'm going, say you already studied the chapter, right? So if at all I'm teaching you something which is not there for you, you can always tell me, sir, this is not there. Okay, so that we can save time, because like me going through the like NCERT textbook, it's been a long time, right? I still remember what not is there, obviously, like whatever is there I know, right? But the problem is me spending time on things which are not there for you, right? So last time also it happened, the titration things were not there for you, right? But still we spent a lot of time, right? So like that, if you encounter anything, please let me know. Okay, right? So as far as titrations are concerned, actually it's very important. It's good that you actually knew it, like how to do it and stuff. Now that you're not able to go to the school and conduct experiments, at least you can know how it is done, right? Okay. So anyways, like that, if I move away uh, from what is required to what is not required, you can always tell me, so this is not there, this is there, all that. Okay. Right. So I think now, okay, I think now we have 13 people. Amazing. Great. So I think we can start, right? Let me share my screen. Okay, my screen is visible. Right. And I wanted to know one thing. Did they tell you anything about coming Friday? You will have extra class for 2 hours. Did they tell you anything? Did any information came from the excellent people?
Yes, sir.
Yes, sir.
Sir
That
sent
they told.
message yesterday.
Yeah, that's what. Like it was suppose. Like I told him that it should be on like last Friday, like yesterday. Basically, it should have been there. But I think they forgot to inform you. Everything was set. I was also ready, but I think they forgot to inform you. So I think that's why they informed it in prior this time, right? So next Friday we will have 2 hours of class again, Saturday and Sunday normally. Okay, fine. So maybe we will just see what we saw last class, because we saw actually so many things, right? Yeah, exactly. This is what it is. So let us look into. Yeah. So we saw what was the problem with Rutherford's model, right? The concept of spectrum came, line spectrum, continuous spectrum, all these things. So then we went on to see how Newton's laws of motion, right? Newton's scientific ideas were actually said that no, it cannot be applied everywhere, right? So we started with what are these black body radiations, what are black holes? Black holes are nothing but black bodies. Okay, so a black body is something which can absorb or release any amount of energy, 0 to infinity, right? That's what the ideal definition says. But I know we are going to little contradicted. Not exactly all energies from 0 to infinity are allowed. Certain energies are allowed, but certain things are not allowed, right? We saw what was those. Okay, so we went on. So what he said is that these are the equations of motion, right? These are Newton's equation of motion. S is equal to ut plus half at squared. B minus u is equal to at. B squared minus u squared is equal to as. All these we already know from our lower classes, right? So when Rutherford said that these electrons are revolving around the nucleus, that means they are moving. So that motion also should be able to obey this particular equations. But what Planck found is that no, it is not going to be like that. They are not following these equations. Okay, if I try to put these equations for the motion of electrons, which is revolving around the nucleus, these equations were not able to aptly, describe the motion, if I have to put it that way. Okay, so based on all this, Planck, we came to Planck's theory. What Planck said is that any atom will contain so many number of these elementary oscillators, Okay. Now these elementary oscillators, when he started the research, he didn't know what is elementary oscillators were. But when when J. Thomson discovered electrons, he understood that these are nothing but electrons. Okay. Now what he said is that if something has to vibrate, I mean, if something has to oscillate or do anything for that matter, it requires energy, right? So that energy E is directly proportional to the frequency of the oscillation. Okay, and we know what is frequency. Frequency is nothing but number of cycles per second. Say if I go in 1 second, how many times I go and come back? Basically, going, coming back is 1 cycle. Like that, in 1 second, how many cycles is what is my frequency? Okay, and I told you frequency is denoted by the letter mu, and it is nothing but the reciprocal of the time period. It is having the unit of per second. Per second can also be written as hertz, H-Z, right? So what he said, since I have E is equal, he is directly proportional to mu, I can get this beautiful equation. This is again, I told you this is a very important equation, right? Till now, whatever energies you saw, right? I think it's mentioned here, E is equal to mc squared, half mv squared, mgh, all contains mass, all the types of energy. This is the only equation where mass is not involved. Right, so that means what? Even radiations, like whichever has frequencies, right? They can also have energy. That's what you have to understand. So E is equal to h nu, where h is Planck's constant. The value is this 6.6 into 10 to the power minus 34 joules second. Okay, now, but the more important point, what he said is that, say I have n electrons with me, right? Say n electrons will have n different energies. He said that all the energies are quantized. Right? We know what he means by quantized. Say I'm going to have one of the electron to have some minimum energy, right? Now that minimum energy is what is going to be quanta. Okay. Now all the other energies possessed by all the other electrons will be integral multiple of this particular minimum value, that is E1, that is what is quanta. So, and say, I think we even saw some examples. If E1 is 5, right? So if I take all the values, only 15, 10, and 20 are allowed. So 12 and 9 cannot be allowed because that cannot be multiples of this 5 joules, right? So E is equal to n h nu is the correct way of writing it. We can assume that h nu is what is E1, n is the integer. Okay, so this is what is me. We already mean by quantization. Something is there, some minimum value. All the other allowed values are integral multiples of this small value. Only those values are allowed. Other values are not allowed, right? So now we understand how black body will not be able to have all the possible energies. There will be, I think I mentioned it somewhere. Did we? Yeah, so I can say here in the box, right? Say E1 will be there, 2E1, 3E1, 4E1, 5E1, 6E1, till infinity it can go. But between E1 and E2, that is between E1 and 2E1, the values which are in between that is not allowed, right? That is what is happening for a black body. Okay, right? Fine. So based on all this, right? Based on all this, this is what is called as Planck's quantum theory. So based on this Planck's quantum theory, only Bohr developed his own atomic model. Okay, so what he said, the main postulates of Bohr's atomic model was that electron obviously revolve around the nucleus, but this time he said that every electron has its own home, right? They are called stationary orbits, right? Now, these stationary orbits are circular in shape, right? Now, there'll be so many number of circular orbits like this electron, nucleus at the center, first stationary orbit, second stationary orbit, third stationary orbit, it keeps on going. Right now, what is so special about the stationary orbit is that as long as electrons stay in their own stationary orbit, okay, there is no loss of energy. Right now, this was the main problem, right, in your Rutherford's model, because electrons are continuously revolving around the nucleus. They will eventually lose all their energy and they will fall into the nucleus. Right now, that problem is overcome by saying the fact that every electron has its own home, right? So as long as they're in their own homes, that is their own stationary orbits, they are not going to lose any energy. Okay, and obviously one more point he said is that the energy of the stationary orbits are quantized. Right? That means you understand the first stationary orbit, second stationary orbit will be twice the energy of the first stationary orbit. Third will be thrice the energy of the first stationary orbit. That's what you mean by quantized, right? Okay. Now, the next point, what he said is the angular momentum, right? Angular momentum we know is m into v into r, right? And momentum is mv. And if at all you want to get any angular quantity, you multiply it with radius, right? So mvr, that is the angular momentum, is also quantized. We said, right? Now, how is it, like, where is the formula? Yeah, here, right? So mvr is equal to nh by 2 pi. Again, h by 2 pi is the quanta value. N into h by 2 pi will become the quantized angular momentum. Okay, right? So, as I told, right, now this energy, like the electron being in its own stationary orbit, no energy, no loss of energy, right? But can absorb energy. Now, please understand, I think, did we speak about this? Where is it? Did we speak? Yeah, so look at this, right? So now say electron is in its own stationary orbit. Okay, now if you supply energy to the electron, now this electron can go to the higher level, right? Is it not? Because say this is E, this next one is 2E, the next one is 3E. Say if I supply enough energy, the electron can go from the first stationary orbit, say, to the third stationary orbit. Okay, so remember, whenever energy is absorbed, right? Whenever energy is absorbed, the electron goes from lower level to higher level. Right? And obviously, whenever the electron comes from higher level to lower level, because obviously the energy is higher and the lower part, the energy is lower. So whenever that happens, whenever that transition happens, energy will be released. Okay. Now I told you sign convention also, hope you remember, the energy absorbed, whenever energy is absorbed, we give it a positive value. And whenever energy is released, we give it a negative value. Okay. So this and all we saw last class, I think. Anything else is there? So yeah, this is about uniform circular motion. All these things are going to happen. How is it going to have uniform circular motion? Two kinds of force will be existing on the electron. One is centripetal force because it is moving along the circle. But the second will be the electrostatic force. Now both of them will be equal, so that only then the uniform circular motion is possible, because the net force, according to your Newton's second law, right? As long as the net force acting on the particle is zero, it can be at rest, or it can continue in this uniform motion. Either it's linear or circular, doesn't matter, right? So with this, we derived the formula. I mean, we didn't derive it. I told you that there'll be a derivation. So this is how the formula looks for radius. Okay, radius of the nth orbital. Okay, Rn is equal to 0.0529 n by z. Angstrom units. Okay, I made a small mistake here. Please change it. This is n squared by z. Okay, I forgot this, guys. This is a small mistake. Please change it. Okay, so Rn, that is the radius of the nth orbit, is equal to 0.0529 angstrom. So sorry, 0.0529 n squared by z. And more importantly, you have to remember that the unit which you will be getting here will be in angstrom units. I told you 1 angstrom is 10 to the power minus 10 meters. Okay, 1 angstrom is 10 to the power minus 10 meters. Please correct this n to n squared. It's n squared, not n. And we know Z is the atomic number. Okay, for hydrogen it is 1, for helium it is 2, for lithium it is 3, so on and so forth. Okay, right, fine. So now we'll continue. We'll continue with today's class. Yeah, any questions?
Yes, sir. Sir, can you show me the slide where you mentioned the two forces acting on electron?
Yeah, sure. One second. So yeah, this is the slide, right? Centripetal force and electrostatic force.
Yes, sir. Here, shouldn't it be centrifugal force?
See, centrifugal force is different, right? So centrifugal force will happen if, like, say, what happens in your mixie, that is a centrifugal force, right? When you mix, like, so when you go for mixie, something is rotating, right? So how do I put it? If I have to give this correct scientific things, right?
So like converting the milk to cream.
Correct. Converting milk to cream. That process, churning, that is centrifugation, we call it, right? But centripetal, you can assume, like, say, you tie, like you hold a rubber band with you one end, the other end of the rubber band is connected to a stone, and you rotate it like this. That is centripetal force. Okay, so it's all about whether the force is pulling inwards or whether the force is pushing outwards. If it is pulling inwards, it is centripetal. Centripetal force. If the particles are trying to move away from you, that is centrifugal force. Okay, yes, so here it is centripetal. Yeah, here it is centripetal only because why? Because the nucleus, right? Nucleus is pulling the electron towards itself, and then it is trying to
electrostatic, right?
Yeah, that is electrostatic. But you see the movement here, it's like what? Here I have tied it, like there is some attraction force. This is like the center point, and I have tied with the rubber band and it's rotating, right? It's very similar to that situation. Is it not? The rubber band here is nothing but the electrostatic force, which exists there.
Sir,
Are you able to get it? I can ask you, not exact. This is not the exact correct scientific explanation, but you can understand what I'm trying to say. Something is connected, the center point and the stone. The stone here is the electron, right? The center point is the nucleus. Okay, so something is connecting between them, and the connection is what is the attractive force. And because of that, it is going to move also, and that is the centripetal force. Yes.
Sir, centripetal force acts inwards, right?
Yeah, centripetal force acts inwards. Yes.
Sir, but already electrostatic is inwards. So if the electron should remain in the orbit, then a force should be acting outside, right? So that has to be centrifugal.
Makes sense, actually. Makes sense.
Sir, so here in this case, electrostatic force is centripetal force.
Electrostatic force is centripetal force? No. It's not like that. It's not like that. Maybe I'll clarify this part. Okay, that's actually very nice question. Obviously, this is moving. Oh, wait. That this is moving inwards, no doubt about it. Centripetal force should point outward. It should point outward.
No, sir, I checked it, sir. Okay. I browsed and I saw that centrifugal force is only acting outward.
Okay, so what I said is right then. So centrifugal force outside, centripetal force inside. So what I told was right. Okay. But in all the books, wherever I've studied it about this, it all mentioned only centripetal force, not centrifugal. But I'll clarify this. Actually, a very nice question. I'll clarify this. Okay. Give me some time. Okay, maybe in tomorrow's class. Right now, tomorrow's class I'll clarify this. Okay.
Fine, sir.
Right. Cool. Any other questions anybody has? Okay. Fine. I think we'll move on to for today's topic. Let me add some page. This is 7th. Okay, fine. So we saw what is the formula for radius, people. Rn is 0.0529 n squared by z angstrom units. This we already saw, right? Now, one more important formula is there. That is for velocity of electron in the nth orbit, right? This is velocity of electron in the nth orbit. Okay, fine. So velocity of electron in the nth orbit, again, there is derivation, people. We don't have to go to it. I can directly give you the equation. You can remember it. So it's 2.18 into 10 to the power 6 into z by n meter per second. This is another formula which you can remember along with radius. Okay. Velocity of the electron in nth orbit is 2.18 into 10 to the power 6. Z again is the atomic number. N is the orbit number, stationary orbit number, and the unit will be in meter per second. Right? Okay. Fine. Now, next important thing is about energy of the nth.
Sir, what is the number? Could you tell again?
It is 2.18 into 10 to the power 6. Okay, 2.18 into 10 to the power 6 Z by N meter per second. That is the value.
Sir, Z represents atomic number.
Yes, Z represents atomic number. Again, it's like for hydrogen it is 1, for helium it is 2, lithium it is 3, beryllium 4, keeps on going. N is the stationary orbit number, whether you're talking about the first or second or third stationary orbit, that number. If first or stationary orbit, N is equal to 1. For second, N is equal to 2.
Sir, and could you explain what is ZE?
ZE, this one?
Yes, sir. It was written inside nucleus.
It was written inside nucleus. Where did you find the ZE, Kana?
Sir, I found it in kinetic energy of electron.
ZE, I think they are talking about, no, if they write just E charge.
Nuclear charge?
I think, yeah, ZE is the nuclear charge. Yes, that's what. Generally, E represents charge, ZE represents the nuclear charge. Yes, absolutely.
Fine.
Okay, right, yeah. So the next thing is energy of the nth orbit. right? Obviously, I told you that all the orbits will have their own energy, right? All the stationary orbits will have their own energy, right? Now that energy is what we are going to see now. That energy En is equal to minus K into Z square by N square. This is again an important equation. I'll tell you what is this K. K is a constant. Okay. The minus sign is also very, very important. Okay. So En, that is the energy of the nth stationary orbit, is equal to some K constant into Z squared by N squared. Okay. It's equal to Z squared by K into Z squared by N squared. Now this K is very important, people. Right. This K, depending on the K value, the unit will change. Okay. Now K value will be 13.6. I'm sorry. K value is 13.6 if, I'm sorry. Okay. 13.6 if I want the energy in terms of electron volts. Remember the units of energy. There are two units for now. All you have to remember. One is electron volts. Another one is joules. Okay, these two are two different units. Okay, so for these two different units, two different constant term K values are there. If you want this energy in terms of electron volts value, then you put the K value as 13.6, right? And if at all you want the answer in terms of joules, you put the K value as 2.18 into 10 to the power minus 18. Okay. Right? If you want the energy value in terms of joules, you put the K value as 2.18 into 10 to the power minus 18. Right? Fine. Now the negative sign, why is it important? I'll tell you. Right? Say, like, if I can understand, I'll like when I explain the next things, when the upcoming things, they will understand why this negative sign is very, very important. Okay, for now, just take it like minus K into Z squared by N squared. K value, two possibilities depending on what unit you want to get the answer for energy, either in electron volts or in terms of joules. Right? Okay, fine. Now, next one I want to know is the transition energy. Okay, next one is the transition energy. Okay, so what do you mean by transition energy? Basically, when electrons shift from one stationary orbit to another stationary orbit. Right? See, please understand. Say this is the first orbit. This is the second orbit. The electron is here. Say the first orbit has energy of E1. The second orbit has energy of E2. Okay. Now, for the electron to go from this orbit to this orbit, what you have to do? Now, the energy should be supplied. Obviously, I told you whenever electron goes from lower to higher level, energy has to be supplied. Right? Energy has to be supplied. Now, how much energy you should supply is what we're trying to understand here. Okay, now this is E1, this is higher energy E2. So can I say there will be some energy difference between these two? Right? Now that energy only has to be supplied. Right? So can I say E2 minus E1 is what is the energy which we have to supply? Is it not? Right? Say if the electron has to go from first orbit to the third orbit, then what you have to do? The energy supplied will be equal to E3 minus E1. Right? That is the energy supplied value. That's exactly what is called as transition energy. For obviously, and it is not only from lower to higher, right? If the electron comes from, say, right, say I'll write like this, right? This is n is equal to 1. This is n is equal to 4. Say the electron is here. It needs to come to the first orbit, right? So obviously this energy is higher. This is E4. This is E1. Now, obviously, if the electron comes to the lower energy state, energy will be released, right? How much energy will be released? Energy released, I can tell that it is again going to be the difference between these two energies. That is E4 minus E1, right? Okay. That's exactly what we're trying to say. The energy released or energy absorbed when the electron shifts from one level to another level. How much energy is released or how much energy has to be supplied for all these transitions from one level to another level. That energy is what is called as transition energy.
Oh,
okay.
Sir?
Yeah.
Sir, when energy is supplied, Then according to the formula En equals minus k square z square k z square upon n square,
Yeah.
energy will be negative, right?
Yeah, exactly. I'll come to that. 1 second. I'll just come to that. I'm coming to the right point, right? Wait for it. I'm going to explain that exact thing only, right? Say now, electron goes from one level to another level. Say it goes from second level to first level. Okay. Sorry. First level to second level it goes. Right? Now, we know energy, obviously energy has to be supplied, right? And I know energy supplied should be a positive value. We already discussed this, right? Energy supplied is positive, energy released is negative. That's what we do in chemistry. Okay, now let us check whether I'm going to get a positive value or not, because I know already what is the energy of the second orbit. If I just put n value as 2 here, I know what is the energy of the second orbit. If I put the n value as 1 here, I know what is the energy of the first orbit. Correct, right? So now if I do that, that is what is my transition energy. I told you, like whatever is the energy difference between the two levels, that is the energy which has to be supplied, or that is the energy which has to be released if the electron comes from higher level to lower level. Magnitude is okay, right? Magnitude is basically the difference between the energy values. Very simple, right? But whether it should be a positive value or negative value will depend upon the energy supplied or energy is released, right? So we'll try to understand here, right? Say now, I have energy, or delta E, I call it, right? This transition energy is denoted by the letter delta E. Okay, right. Now, delta E will be what? E1 minus E2. Okay, right? That is first energy level. I have to go to the second energy level. Is it not? Right. Now, if you do that, what is E1 value? It is basically minus k z squared by n squared, right? Minus k z squared by n squared. So I will write my E1 as minus k z squared. Okay. Same way, I can write my E2 value as minus k z squared divided by 4. No problem. Okay, because it becomes n squared now, right? Minus k z squared by n squared, n is equal to 2 now, so it becomes 4. Right. Okay. Now, if you do that, if I write E2 minus E1, sorry, E1 minus E2, right? I will just check whether we have to take E1 minus E2 or E2 minus E1. Okay. Whichever gives me a positive value, that value I take. Okay. Fine. So if I do E1 minus E2, that is basically kz squared minus k minus of minus kz squared divided by 4. Right. So what will happen? So if I just take kz squared common, right? If I just take kz squared common, now here it will be minus 1, right? Now this is already plus 1 by 4. Okay, so basically what? It is 1 minus 1 by 4, which is basically 3 by 4, right? So what I'll be getting is minus 3 by 4 kz squared. Now what are you getting as a negative value? Obviously that means what? You should not be taking E1 minus E2. You should be taking E2 minus E1, final minus initial, or higher orbit minus the lower orbit. That's what you have to understand. Okay, whenever the electron goes from lower level to higher level, higher orbit minus lower orbit. Not only for this case, for any case, always remember this, right? Delta E is higher orbit minus the lower orbit. Right? It is not about whether electron, see, it's not about initial orbit and the final orbit. It's not like that. It is higher orbit, whichever is the higher value, that value, higher stationary orbit, that minus the energy of the lower orbit. It is always going to be like that. Only then you will get the correct sign. Okay, see, you are doing a lower orbit minus higher orbit, and that's why you're getting a negative sign, but I should be getting a positive sign, because the electron goes from lower level to higher level. I'm going from first to second, right? If I come from second to first, then I do this thing, E1 minus E2. Okay. Anyways, do not worry about the sign so much. Okay. It is not going to be this value delta E will not be using it like this. There is another way of using it. Okay. We'll discuss about this. Okay. All you have to understand is the transition energy is not the energy is nothing but the energy difference between the two stationary orbits. That's it. And you know what is the energy of the nth stationary orbit? That is minus kz squared by n squared. Okay. Do not get confused with the signs here, right? Because this delta E, we will not be using it in this way, right? We'll be using it in some other way. Okay. Or you do either E1 minus E2 or E2 minus E1, doesn't matter, right? But you know how the value should be, right? Like you do either this or this. Now, say for example, you got a negative value, but you know the electron is going from lower orbit to higher orbit. Again, I give you a situation. See, it is going from first to second, but you're getting a negative value. If you get that, obviously that means what? You should do the opposite one. Say instead of if you did E1 minus E2, you should have done E2 minus E1. That's what you need to understand. Okay. So first you do either E1 minus. One second. So either you do E1 minus E2 or E2 minus E1, doesn't matter. At the end value, you see what is the sign, right? If the sign you got and the transition, whether it is going from lower to higher or higher to lower, depending on that, you change the sign. Very, very simple. Yes, please tell me what is the doubt.
So then why can't we say final orbit minus initial orbit?
If we say final orbit minus initial orbit, will it work? In this case,
yes.
Yeah, I should.
So if we say like that, then correct answer will come.
One second, we'll check it out. Okay, so here the electron goes from first orbit to second orbit. Okay, I am assuming like that, first orbit to second orbit. So if I do final minus initial is final is E2 and the initial is E1. Okay, then I'm getting a positive value if I do E2 minus E1. Or if I get if I go from second to first, I should be getting a negative value. In that case, I do E1 minus E2. Yes, absolutely, it works. Actually, we can take it like that, right? And avoid all the confusions. Actually, we can do this. So always remember, people, you can always write the transition energy delta E as final energy or final energy minus initial energy.
Sir?
Yeah, please tell me.
Sir, but then after the electron goes into the excited state, it is again going to return, right?
Yeah, correct. Absolutely. But the problem is, it will not say, for example, this is the first level, this is the fourth level, assuming like, let's say electron was here initially, it went to here. Now the electron is here, right? Now, when the electron comes back, right, it will not come back directly to the first orbit. It will never happen like that. Say it will go to the third orbit, then from third orbit, it can jump to the first orbit, or say from the fourth orbit, it can go to the second orbit, again come from the first orbit, right? So if you're trying to say that the energy released or say the energy supplied, will it be equal to the energy released? Because say energy supplied, the electron goes to the higher level. Now the electrons comes back, it is coming back in the same way, right? So I mean, same Vincent is coming back to the same level. So will the energy released and energy supplied be same? Absolutely not. It will never be the same. Why? Because when energy is supplied, the electron directly jumps, no doubt. Right, but when the electron, this is what generally happens. When the electron comes back, and it obviously excited state, it has to come back. It will not directly jump from 4 to 1. It will go to, say, it can take any path. One of the possible transition is 4 to 1 directly, but there are other multiple paths available. Say 4 to 3, then 3 to 2, then 2 to 1, or say 4 to 3, then 3 to 1, or 4 to 2, then 2 to 1. Multiple paths are available, and all paths are possible. There is no restriction like that. Only this has to happen, or that has to happen. Right? So always remember the energy supplied, that is when the electron goes from higher energy to lower energy. Obviously, the electron comes back, but it is not exactly the same way it went up. Right? So these two energies are not same. Always, like at least 99.999%, it wouldn't be same. Okay?
Okay.
Is your question answered? Yeah, please tell me.
Yes, sir. Is there any reason why the electron returns back to the ground state?
Oh, I told you, right? So everybody has their own home. Say, for example, the electron is comfortable in the first orbit. Okay, the electron's home is first orbit. So if you're going to excite it to the second level, obviously it is unstable there, right? But some electron will be stable only in the second level, right? This is the first level, second level. The electron's ground state is only the second level, right? Then obviously, if you're going to keep it in the first level, again it is unstable. Hope you're understanding what I'm trying to say, right? Every electron has its own home, right? And if it is not going to be in its own home, either the lower orbit or the higher orbit, it is always unstable. Okay.
Okay, sir.
Right? It is all about the energy concentrations. Only if if the electron's home is second level. Now, why is it like that? For this electron, this much energy should be possessed by that particular orbit. Only then it is stable. If the energy supplied or the energy of the stationary orbit is not going to suit it, obviously it becomes unstable.
Sir?
Yeah.
Sir, then how are ionic bonds?
How are ionic bonds? You're trying to say something. I'm not able to hear Kanna, only.
Can you hear me now, sir?
Yeah, now I can hear you. Yes, please tell me.
Yes, sir. My question was, how are then ionic bonds?
Again, ionic bond after that is cutting. Can you put it in the chat box? I'll put it in the chat box.
Okay, sir.
Yeah.
Sir, why do we specify it as stationary orbits? Are there any other orbits which aren't stationary?
Actually, why he has to put the name stationary orbit is because he wanted to tell in the sense that electrons are not going to lose any energy. That's the thing he wanted to mention. But like when he developed this theory, the entire idea was different. But now what we have, it's actually very dynamic, right? We call something called as an orbital. That orbital itself, we say it is a wave. It is not even an orbit, right? It is not a perfect, circle or something. It is actually very dynamic. It's in the form of a wave, right? So this would all are primitive, like say when the early stages, he just wanted to specify the point that electron will not lose energy as long as it stays in its own stationary orbit, right? That for that only he specified this term stationary, right? He wants to mention that the electron maintains its stationary, or stationary in the sense the uniform circular motion. That he wanted to mention. How the uniform circular motion will happen if all the energies are cancelling each other. That's why he wanted to mention that stationary orbit. Nothing else. No specific reason as such.
Thank you.
Yeah. Is the question there in the chat box? How are ionic bonds formed? Like an electron is given to another atom and it revolves around some other orbit in the second element, so it will be unstable, right? Okay. See. Okay. If I have to answer this question, I have to assuming the fact that this chapter is already completed for you, everybody, this in school.
No, sir. They are going to complete it by Tuesday.
Okay, so everybody has some idea about orbitals, right? S orbital, P orbital, some idea? Is it there?
Yes, sir.
Okay, some basic idea is there. So what? I think it was. Once again, it was. Yeah, Subrajit, what is he asking is, so when, say, for example, I have sodium chloride, Na plus and Cl minus, sodium would have lost electron, and this electron would have gotten into chlorine, so that it would have formed Cl minus, right? So he's asking, so obviously electron would have stayed in, inside sodium, it would have been stable. Now, if it loses its home and goes inside chlorine, so how it is going to become stable? Is that the question? I think that's what I understand from the question. So what you have to understand is, you see, sodium, I have 1s2, 2s2, 2p6, 3s1, and I still have 3p0, right? The p orbital is still empty. Now, you check, right? Okay, you check where the electron is going. Okay, where the electron is going inside this, it will actually go into the 3p orbital. Okay, it will actually go into the 3p orbital. Or forget about this S and P. If I write the configuration as 2, 8, 1 for sodium, the configuration was 2, 8, 7 for chlorine, right? So this one electron is what is lost and it came here. Now, what you understand, the electron was in the third orbit. Here also it is the third orbit only. So it is stable, right? It doesn't matter which element it is. For this electron, it was in the third orbit for sodium. As long as it exists in the same third orbit for chlorine, no problem, no issues, right? But if there are so much energy differences, say the electron comes from third orbit, right? And the electron moves into the fourth orbit of the second metal. Yeah, it is unstable. Definitely it is unstable. right? But this particular scenario you see, the electron comes from the third orbit, goes into the third orbit of chlorine, right? So obviously it is going to become stable. Okay, I hope I answered your question, Subhrajit. Right? Okay.
Sir, here.
Sir, is there any compound like where the electron does not go into the same number orbit?
Yeah, if you take, if I have to take potassium chloride, right? So potassium's electron will be there in 4s and it is going to go into 3p, right? Again, this will be happening. But see, for this to become stable, there are various other reasons. When we go to the chapter called as chemical bonding, that is the, after this chapter, we'll go into periodic table. After that, we'll move to chemical bonding chapter. At that time, I'll explain you in detail how exactly all this is going to happen. Okay, right? So for now, yeah,
okay, sir.
Your question is valid. If the electron goes into the next one, it should be unstable. But what I can understand is there is something called as octet rule. Correct, right? There's something called as octet rule. Now, when I compare octet rule, obviously octet rule gives me stability, right? So what happens is even if the electron goes from 4s to 3p, since for both of them, the octet is getting satisfied, is it not? If the electron lost here, this becomes octet satisfied. If the electron goes inside this becomes octet satisfied, right? So eventually the stability attained will be way more than the simple thing that the electron is going to two different orbits and that becomes unstable. That is a very negligible instability compared to the stability attained with respect to the octet rule. Okay,
sir, I have another doubt, sir.
Yeah, please tell me.
Sir, can you hear me now properly?
Yeah, I can hear you. Tell me. Yeah.
Yes, sir. Sir, as you said, the energy level, as Bohr said, sorry, not Bohr. Okay, when some guy said that the energy level of one orbit is fixed. So
okay.
the atom, like the electron, does not spiral and collide into the nucleus.
Okay.
So, but then how can the energy level of suppose one like first orbit be the same for all the atoms?
Yeah, absolutely, it will be same. How it will be same is it doesn't matter. See, it's all about electrons. Whatever be the atom, right? The nucleus will be same, right? And one more important thing is this particular Bohr's theory, right? This Bohr's theory will work only for single electron species. Right? This will work only for single electron species in the sense that for hydrogen it will work because it has only one electron. It will not work for helium, but it will work for helium plus. And same way, it will not work for lithium, but it will work for lithium 2 plus. Okay, only for these kind of species, right? The the Bohr's theory works. Okay, so if you look at it in that way, everything contains only one electron. Right, so that means what? The atom almost remains the same, like almost it remains the same only. So the distance, say from nucleus to the first to second to third, the distance, say this is R1, R2, R3, all of them will be same. Right? Obviously, we even saw that, right? We even saw that. Just that it's going to be in terms of this thing. What is that? The atomic number is also included. Right. So for a particular energy level, yes, it is going to be very similar. Now, your question is, yes? If something ask something?
Yes, sir. Sir, in this very example, suppose lithium has 3 protons, right? So it will attract the one electron which is in the first orbit more close to it. So how is the radius same?
Exactly. The radius will not be same. If you look at the formula for radius, what we started with, right? It is 0. Whatever, like forget it. It's n squared by z. Now this z takes care of it. Z is the atomic number, right? Right. Now that z takes care of the radius. Okay. So your question is,
then the
if the
velocity.
Please tell me. Go for it. Velocity.
Yes, sir. Sir, not velocity. The energy of the first orbit in case of lithium will be more than that of hydrogen, right?
Yeah, according to the formula, if you see, it is z squared. But yes, absolutely. First orbit of lithium will have more energy compared to the first orbit of hydrogen. Yes, absolutely. Yeah.
Sir, then if suppose in the case of ionic bond, which you told NaCl, so the atom, the electron which is present in the M shell of sodium is going to the M shell of chlorine, but number of protons differ, right? So the energy also differs.
Absolutely. Energy differs. Absolutely. That's what I'm telling. What you have to concentrate on is like, yeah, obviously this maybe brings instability. The electron was here. It was here. It would have different environment. Now, if it goes inside chlorine, it will have different environment that might or might not. Most probably, it might give instability. Right? It might become unstable. But what you have to understand is, you remember this octet rule. Right? Now, octet rule will bring in stability. Right? So the stability it brings in is way more than the instability which we are talking about here, because of the electron's environment is changing. Right? So thereby overall effect, what will you see is that this becomes stable. Right? Because the stability is more than the instability which is created because of this transition of the electron. Right? So overall, what will you see is that both sodium and chlorine would have gotten stabilized and the compound would have been formed, NaCl. Yes, that makes sense?
Yes, sir.
Okay, right, cool. Fine. So what we are talking is, this should have come only in the last, after I finished the Bose theory, but not a big deal, right? You can know that it works only for single electron species. It doesn't work for species which are having more than one electron. Bose theory doesn't work for that. This is one of the drawbacks of Bose theory. Okay, right. So we saw about transition energy. It is nothing but you can always remember it as, where we wrote it. You can always remember it as, where is it? Yeah, final minus initial. Where did we write?
Sir, there's a delta E.
Yeah, delta E is okay. Okay. Final energy minus initial energy. Yes, absolutely. Right. So wherever the electron finally goes, that energy minus initially where it was, that energy you subtract, you don't have to worry about the signs, right? You will directly get the value of delta E, transition energy. Okay. Right. So transition energy, you know how to find, right? It's basically E1 minus E2. I mean, final minus initial. You just have to put the final E. You know how to calculate the individual energies, which is nothing but minus kz squared by n squared. That formula you use. Find the two energies and subtract them. You are going to get the transition energy. Okay. The next concept, what you have to understand is this ionization energy. Okay, the next one is what is called as ionization energy. Okay, fine. So now if you take ionization energy, right, how do we define it? We already know ionization energy definition. What is the definition? Can someone tell me what is the definition of ionization energy? From what we know, lower classes, in 10th, I don't know that you studied this, but if you have studied this, someone knows what is ionization energy?
The energy required to ionize an atom.
Ionize an atom. Okay, yeah, that's the okay. That's one form of putting it. But if you have to go to the correct definition, the modern definition, if you look into it, right? If you look into the modern definition, it says it is the energy required to take out an electron. Right? It is the energy required to take an electron out from the valence shell. Right? Say, you know what is valence shell? Valence shell is the last shell. Right? So what does the modern definition says? The modern definition says that it is the energy required to take the electron from the valence shell of an atom. Right? So basically, for sodium to become sodium plus, I have to remove this electron. Now this electron would have came from the valence shell. So obviously would have supplied some energy into this for me to remove the electron. That energy is what is called as ionization energy, IE. Okay.
So then why not add electron?
Yeah, adding electron, I have some other term. It is called electron gain enthalpy, EGE. EGE is electron gain enthalpy. Right? When you add electron to the valence shell, some energy will be released or some energy will be absorbed depending on the atom. That energy is what is called as electron gain enthalpy. Ionization enthalpy is only for
but energy is required to add an electron in an atom.
Depends. If at all you have, elements like chlorine, fluorine, all these stuff, when you add electron, they become stable, right? So they will release energy. But say you have a metal like sodium, right? Now into this, you want to add an electron, it is very, very, very difficult, right? So for this, you have to supply energy. So it's depending on the atom. If the atom is welcoming the electron, it's okay. The energy will be released. If the atom is going to repel the electron, right, then you have to make it go inside the atom, even though it suffers repulsion. So you have to supply energy for that. So it depends on the atom, whether you're adding electron, energy will be absorbed or released.
Okay, sir.
So will it be negative?
Yes, and obviously energy released will be negative. Now this value will be positive. This will be common. Energy released is negative, energy absorbed is positive. Always. Okay, right. So this is the modern definition. Modern definition says it is the energy required to take out an electron from the valence shell. Okay, but when Bohr gave, he didn't say it like this. Very similar, right? But we'll give the proper definition. And I can take you the definition, what Bohr said. This is the normal definition, which we'll again see in periodic table, right? We'll again see this definition again. But for this chapter, right, the definition is different. Please take the definition. Actually, and before this, guys, actually, I can give a proper formula for delta E. Now, delta E, I told that it is EF minus EI. That is final energy minus initial energy. Okay, so if you keep that in mind, this delta E, the formula becomes very easy. Okay, kz squared divided by 1 by nf squared, sorry, ni squared, because I have a negative sign already. Right? It will become 1 by ni squared minus 1 by nf squared. This formula you can remember for transition energy. Okay, kz squared into 1 by ni squared initial stationary orbit minus 1 by nf squared final stationary orbit. Okay, right. Now, if you're ready with this, then we can go for the definition of ionization energy with respect to Bohr's theorem. Please take down. Okay, so.
Sir, could you show the formula once again?
Yeah, sure. Formula is this. Delta E is equal to kz squared into 1 by ni squared minus 1 by nf squared. Okay, right. So let us take to the definition.
Sir.
Definition. Please tell me. Again, I'm not able to hear. Some problem is there. Okay, fine. You can put in the chat box now if you have any doubt. I'm not able to hear you. Right. So the definition goes like this. It is the amount of energy required. It is the amount of energy required to move the electron, the first orbit, to move the electron from the first orbit to the infinite orbit. Okay, I'll repeat the statement. It is the energy required to move the electron from the first orbit to the infinite orbit. Okay, basically infinite orbit means out of the atom. Like that's what it means, right? Okay, so that's the definition. Very simple definition. The first orbit, say from the first orbit to the infinite orbit. From the first orbit, electron is there. It has to go to the infinite orbit. How much amount of energy you supply? That is what is called as ionization energy, according to Bohr. Right? So obviously you see that there's a subtle difference between the ionization energy definition of Bohr with the ionization energy what we have now in modern days. Right? Now we say ionization energy, say for example, this is the valence shell. Third shell is the valence shell. From this to infinity, that is the ionization energy we currently use now. But whatever be the type of atom, according to Bohr, from the first orbit to the infinite orbit, what is the energy required? That is what is ionization energy. It is not from valence shell. This is the modern definition. Modern definition contains valence shell, but your Bohr's definition contains only the first shell, not the valence shell. Okay, right? Now I'll be able to derive a beautiful formula for ionization energy, i.e. from the transition energy itself. I can just use this formula. Now, what is Ni? Ni will be 1 initial orbit. What will be NF? NF will be infinity. That is the final orbit, right? So keeping that in mind, I can easily substitute it. So I have IE is equal to kz squared into 1 by 1 squared, Ni squared. Ni is 1, initial orbit is 1, minus 1 by infinity squared. NF is the NF is the infinity orbit, right? Now 1 by infinity is 0 basically, approximately, right? Infinity is a very large number. So 1 by infinity will become 0. So what you have here is IE, that is the ionization energy, is equal to K into Z squared. Very, very simple. Okay, ionization energy is equal to K into Z squared, right? And please remember, if I ask you, right, to find ionization energy of helium, if I ask you to find the ionization energy of helium, tell me, think properly and tell me whether I can use this formula or not. If I ask you to find the ionization energy of helium, or I'll give you one more clue. If I ask you to find the first ionization energy of helium, will you be able to find this with this formula? Think about it and tell me.
No, sir.
Why?
Sir, because helium already 2 atoms are filled, sir. That is the first in the first orbit, and like if elements are if the electron is added, it will become unstable, sir.
No, not like that. The reason comes from the drawback of your this thing. I told you that this will work only for single electron species. Okay, helium, if I say, right, helium contains how many electrons? It contains 2 electrons. So for this, you cannot use the formula. Please remember. But if I ask you, find the ionization energy of He plus, then okay, you can use the formula because He plus contains only 1 electron. Or I can ask the question like, find the second ionization energy of He. If I ask you, again, it's okay. Why is it like this? Please look at this. He will become He plus by losing an electron if I supply the first ionization electron. Basically, it contains 2 electrons. Now it will contain only 1 electron. Removing the first electron, we cannot use Bohr's, right? But He plus becoming He2 plus by removing another electron. For this, you can use kz squared formula. Hope you're getting my point. This is my second ionization energy. Okay, first ionization energy will be first ionization energy will be for the first electron. Obviously, for that we cannot use because He will contain 2 electrons. For that, I cannot use Bohr's. Now, after the first energy is supplied, and then you form He plus, which contains 1 electron. For this, if you want to find the second ionization enthalpy of helium to become helium-2 plus, for this you can use the kz squared formula. Okay, so either I tell find the ionization energy of helium, or if I tell you find the second ionization energy of helium, it's okay. I mean, it's ionization energy of helium plus or the second ionization energy of helium is okay. But if I just roughly tell you find the first ionization energy of helium or generally the ionization energy of helium, you cannot use the kz squared formula. Yes. Any questions? Someone who wants to ask any question?
Sir, can you hear me?
Yeah, I can hear you. Tell me.
Yes, sir. So in the formula of delta E, what does N?
What does N specify? N specify the orbit number. Say if the electron goes from, where is it? If the electron, say for example, electron goes from first orbit to second orbit, okay, Ni will be 1, Nf will be 2. Same way, if the electron goes from second orbit to first orbit, Ni will be 2, Nf will be 1. Initial orbit to the final orbit. What is the orbit number? These are what is Nf and Ni. Okay, understood?
Yes, sir.
Right? I think there's some in the chat. I think some question. Oh, that's the same question you asked. Okay, cool. Right.
Sir,
I hope
so
everything
this
is clear.
formula won't be applicable for He3 plus also.
He3 plus, how will it exist, man? After
Oh,
He2
sorry,
plus,
sir.
there's no electron, right? Yeah. Okay. Right. Say the same question can be asked. If I ask you, the question is applicable. You can use this case. That's IE is equal to kz squared, not minus kz squared, plus kz squared only. Kz squared for, say, I can ask you to find it for second ionization energy of lithium. Or I can ask you to find the ionization energy of lithium 2 plus. For both of them, it's okay. But if I tell you, find the ionization energy of lithium, no, you cannot use this formula. Okay, right? Be very careful. All you have to remember is that Bohr's theory will work only for single electron species. So all the formulas, radius, velocity, energy, transition energy, ionization energy, all these formulas will work only for single electron species. Remember this.
Sir, isn't it
Okay.
third ionization enthalpy?
Okay, first lithium will contain three electrons. After the first, it will become Li plus, which will contain 2. After the second, it will become Li2 plus, which will contain 1. So, yeah, third, obviously. Right? It should be third ionization energy of lithium. Absolutely. Yes, correct. Okay. Right. So, anyways, you understood the point. The point is that that particular species should have only one electron. Then only it will work. Okay. Right. Fine. So that's about any other formula is left out for Bohr's? No. Right. Fine. So now what we do is, what is the time? Okay. We have half an hour. We'll do some problems on all the formulas which we saw. Okay. We have 5 formulas. Remember, I think I can just write it down so that you can also have R is equal to 0.0529 n squared by Z Armstrong units. Velocity Rn here, okay, velocity of the nth orbit, I mean electron in the nth orbit is 2.18 into 10 to the power minus, I forgot. Great. See, even I am forgetting. So it is very natural for you to forget, people.
19.
10 power 6. 10 power 6. Right? Okay. 10 to the power 6, not minus 6, plus 6. Okay. So Rn is this, Vn is 10 to the power 6, Z by n meter per second. En is equal to minus kz squared by n squared. Again, k value 2 possibilities, 13.6 if it is electron volts. K value is 2.18 into 10 to the power minus 18 if you want the answer in terms of joules. Next is transition energy, delta E, that is kz squared into 1 by n I squared minus 1 by n f squared. Initial orbit minus final orbit. Lastly, ionization energy, IE, is nothing but kz squared. Very, very simple. Okay. So from Bohr's theory, if question has to be asked, it will be asked only from these 5 formulas. Questions means for problems, numerical problems. Okay. Right. Fine. So let me bring some problems for you. Just a moment. Just looking for the correct problem to be given. Okay, fine. We'll take the problem like this. Please check on the question, people. Determine third Bohr's orbit's radius. Determine third Bohr's orbit radius. Third Bohr's orbit radius for He plus ion. Determine the third Bohr's orbit radius for He plus ion. Okay, the question is very simple, right? You have to find the third orbit's radius for He plus ion. Go, tell me the answer.
Sir, 2.3805 into 10 to the power minus 11 meters.
Okay, it's correct, I guess, right? And guys, I did a very small mistake again. I'm so sorry, keep on changing things. This is not Angstrom units, okay? This will be in nanometers, okay? And please understand, 1 nanometer is 10 to the power minus 9 meters, right? I told you this Angstrom units, if it's there, it becomes 10 power minus 10 meters, but just 1 decimal point will be different here. Please change it. Okay, Rn is equal to 0.0529 n squared by z. The answer you will get in terms of nanometers, not in terms of Angstrom units. Okay, please change it, guys. Okay, please change it. Again, I'm repeating, please change it. It's not Angstrom units, it's nanometer. 1 nanometer is 10 to the power minus 9 meters. Okay, now it's just formula. You have to simply substitute the formula. So yeah, the
0.23805 into
nanometers. Yeah.
Nanometers.
So I just 1 second, guys. There's some background noise. Just give me a moment. I'll do it myself. Okay, little better. Right. So I just have to substitute in the formula. They're asking for third orbit. So basically n is equal to 3. And they're asking about helium plus. So obviously for helium, the Z value is 2. Right? The atomic number of helium is 2. Right? So it's substituted. So R3 will become 0.0529 into n squared. N value is 3. So 3 squared divided by Z. Z value is 2. Okay. So 3 squared will become 9. So answer you will be getting would be 0.238 nanometers. This is what you will get the answer is. Okay. Right? Very simple. Direct form of substitution. Okay. Fine. Actually, I would have asked you the same question. Find the velocity also. Okay. Velocity of electron in the third orbit of helium plus. Okay. You found out R3. Find out V3 for this. Same question. Find
the 3.27 into 10 to the power 6.
3.27 into the power 6.
Sir, 1.45 into 10 to the power 6.
That's the correct answer. Yeah.
Sorry, sir. I reversed the ZN.
Z by N you put as Z at okay.
Yes, sir.
Yeah, that's a common mistake that happens. Yeah, right, again, a simple formula, people use the formula which we have to use 2.18 into Z by N. Again, Z values 2, N values 3. So if you substitute, you will get the V3 value as 1.45 into 10 to the power 8 meter per second. This is what will be the answer. Okay, right, easy questions. Now let us make it a little more interesting. We will just solve a little more difficult question. If you are ready. Take on the question, people. Determine the orbit number. Determine the orbit number of Li2 plus ion. Determine the orbit number of Li2 plus ion in which an electron is moving. In which an electron is moving at a speed equal to the speed of electron in the first orbit of hydrogen atom. Speed equal to the speed of electron in the first orbit of hydrogen atom. Okay, I'll repeat the question, people. Determine the orbit number of Li2 plus ion in which the electron is moving at the speed equal to the speed of electron in the first orbit of hydrogen. Right? Hope you understand the question. Anyways, you try. I'll also help you after someone says me the answer. And I'll mute myself, people. I know there's a lot of background noise. This is RD, right? Month. Tamil month of RD. Yeah, 3 answer. Yeah, correct. 3 is the answer. So this RD month, there'll be like near my home. There's a temple, Amman temple. So obviously it is going to be very famous, or it will be like a Tiruvizha here. A big function will happen. So they started putting music and stuff. Because we have only less time. We have just 15 more minutes. Very simple problem again, right? So maybe I'll give you 1 more minute for anybody else if they want to try giving me the answer.
Yes, sir, 3 only.
Yeah, okay. I hope everybody's trying. Very simple. So what they're telling is they have to find the N value for Li plus ion, right? There is one electron in some nth orbit. Okay, there is an electron in the nth orbit which is moving in the same speed, say Vn for lithium plus. Okay, there is some electron in the nth orbit that is moving with some velocity. Now, what is the velocity? The velocity is equal to the velocity of electron of hydrogen, which is there in the first orbit. Very, very simple. This, if you understand from the question, that's it. It's just formula substitution. Okay, again, I repeat. There is some electron in the nth orbit, some n orbit for Li plus. Now that is moving in the same speed as this electron, which is there in hydrogen, and where it is there in the first orbit of hydrogen. Okay, so Vn of lithium plus, how do we write it? It will be 2.18 into 10 to the power 6 Z by N. By Z is Z for lithium is 3, and we don't know, right? N only we have to find, right? Which is equal to again 2.18 into 10 to the power 6. How much for hydrogen into Z by N? Z is 1, N is also 1. Very simple, right? Because they told it's first orbit, and I know for hydrogen atomic number is 1. So 2.18 into the power 6, 2.18 into the power 6 gets cancelled. So what I'll be getting is 3 by N is equal to 1. So I'll get the N value as, that's it. Very simple. Okay, right? Okay, we'll move on to the next question. Okay, second the question. Determine the second ionization energy of helium. Determine the second ionization energy of helium. And I want the answer in terms of electron volts. Okay, I want the answer in terms of electron volts, not joules. And guys, if in the exam they don't give you anything about the units, you by default they're asking for joules because that is the SI unit. Okay, in your exam, in your school exam, if they don't specify anything about the unit, remember that by default it is joules. Now I'm specifying that I want the answer in terms of electron volts. Okay, but if I don't tell you anything, you do it only for joules. I should mute myself. It is very disturbing for you if you're doing your problems.
Sir, 8.72 into 10 to the power minus 18 joules.
Sir, 54.4 electron volts. Sir, you are in mute. Sir.
Oh, sorry, I'm sorry. Right. So I'm telling your answer might be right, Suprajit, I think, but I want the answer in terms of electron volts. So the answer is, yeah, answer as you told is 54.4 electron volts is the answer. If answer is coming in electron volts. Okay.
Yes, sir, I'm getting same answer.
Okay, good. Right. So ionization energy formula is very simple. It is K into Z squared. That's it. Now I want the answer in terms of electron volts. So the K value is 13.6. And for helium, the Z value is 2. So it becomes 2 squared. So we'll be getting the answer as 54.4 electron volts. Okay, right? Fine. What is the time? Okay, we still have this thing. Guys, I want to tell you one thing, right? According to the Planck's equation, right? I wrote E is equal to H nu, correct? Right? E is equal to H nu. Okay. Now I told you that this is applicable for waves, right? Now please understand, if I want to understand what is this frequency for a wave, this is what I see, right? Say, now this is one cycle. Okay, starting from this point and ending in the x-axis. This is one cycle. Okay, say like this. In 1 second, how many cycles I undergo is what is my frequency. Like say, in this is until this point, right? Until this point is 1 second. Okay, so I told you that this is one cycle. Right now, the second cycle starts from here and again ends here. So I would say the frequency is 2 Hertz. You can see the first cycle till this point. Now from this point till this point, there is another cycle. So until I told you is 1 second. In 1 second, how many cycles like this I go is what is my frequency. Okay. Now there is another aspect of the wave you have to understand. Okay. So if I draw like this, say this is the wave. Okay, right. Now, the maximum part, you see, the wave goes to a maximum and it goes to a minimum. Correct? The wave goes to a maximum and also it goes to a minimum. Again, what will happen? Maximum, minimum, maximum, minimum. The cycle keeps on going. Correct? So there is this term called as wavelength, right? As you know by the letter lambda. Okay, lambda we write like this. Okay, for a wave, there is a property. There are two properties of the wave. One is the frequency, that we know, that is number of cycles per second. The other one is the wavelength. Now, what do you mean by wavelength is, before we see what is the wavelength, let me give you some technical terms. Okay, the maximum value is what is called as crest for a wave. Okay, the maximum value is what is called as crest for a wave. And the minimum value what you get is what is called as trough for a wave. Okay, crust, maximum value, trough, minimum value. Okay, so when I say wavelength, right? When I say wavelength, see, this is also a maximum value, this is also a minimum value. Okay, so wavelength is the distance between two crests or two troughs. Again, not to any two consecutive troughs or two consecutive troughs. Basically, the distance between the first crest and the second crest is what is by lambda. Very, very simple. Okay, the distance between the first crust and the second crust, not the first and third or first and fourth, only the first and the second. Between the first and the second, what is the distance between them? That is what is called as wavelength. Or it can also be the distance between this and this area. Between this first trough and the second trough, what is the distance between them? That again is the wave. They'll have same value because it's cycle, right? Normal wave it is. Okay, so wavelength is nothing but the distance between two troughs or two consecutive troughs, crests. Okay, that is what is called as wavelength. Now, this frequency and wavelength are connected. Okay, this frequency and wavelength are connected. Now, how it is connected is by a formula. Frequency is equal to C by lambda. This is the frequency. This is wavelength. And this C is the speed of light. Right? This C is the speed of light. Okay, we know the value. The speed of light is what? 3 into 10 to the power 8 meter per second. Okay, that's a constant value. Okay, so you have to remember this value. I mean, you have to remember the formula. Frequency mu is equal to C by lambda. Okay, so we already have one equation in terms of energy, frequency, that is E is equal to h nu. Now, if I use this formula, I'll be able to get one more energy equation, and that would be E is equal to hc by lambda. Very, very simple. Both the formulas are very, very important. And sorry guys, that is part of background noise. I'm so sorry. Okay, so E is equal to h nu. Now I know nu is equal to C by lambda. Lambda is the wavelength, C is the speed of light. So E again the E, write the E as E is equal to hc by lambda. Okay, two equations for energy. What is the time? Okay, now this transition energy we saw, right? Sorry, the transition energy we saw. This is some energy value, correct? This is some value of energy. Now again, this transition energy can again be written as hc by lambda, or it can be written as h nu, whatever it is. Is it not? Because this is some energy value. Okay. Now this energy will again be equal to some hc by lambda. Now they can ask the question like this: find wavelength for an electron going from first orbit to second orbit. They can ask the question like this. Instead of asking like find the transition energy for the transition of electron from first to second orbit, they can ask you the question like find the wavelength of the transition for the transition from first to second orbit. Now what you have to do is nothing but write hc by lambda is equal to kz squared into 1 by ni squared into 1 by nf squared. Okay, now this lambda is what we have to find. I know h is a constant, c is a constant, right? I know h is 6.6 into 10 to the minus 34. C is some 3 into 10 to the power 8, right? So now I'll be able to get an easy equation for us to remember, right? The equation goes like this. So if I write hc by lambda is equal to kz squared into 1 by ni squared minus 1 by nf squared. Now I know this h is a constant, c is a constant, k is a constant, everything is a constant, right? Now I can write 1 by lambda is equal to k by hc will come. All these are constants, right? Now I'll be getting a beautiful equation. I'll be getting some constant, some other constant. I'm going to call it as RH z squared into 1 by ni squared minus 1 by nf squared. This RH is what is called as Rydberg's constant. Okay, this RH is what is called as Rydberg's constant, and I'll give you the value for Rydberg's constant. Just a moment. Okay, the RH value is 1.097. Right, 1.097 into 10 to the power 7 per meter. Okay, meter per minus 1, that's the unit. Okay, hope you all understand. I did nothing. I know E is equal to hc by lambda, so I wrote delta E as hc by lambda, which is equal to k z squared into 1 by n squared minus 1 by n squared. H is a constant, C is a constant, K is a constant. Right? So if I substitute the value here, what you'll be getting is basically some other constant, and that constant name is Rydberg's constant. Okay, and that value is 1.097 into 10 to the power 7 per meter. Okay, so we'll stop with this for today, people. Now today, next class, tomorrow's class, we'll be solving problems on all of this. Okay, and there are a few more interesting stuff coming on the way. Okay, so if there are any other questions anybody wants to ask me anything? Okay. So
sir, can you show the value of Rydberg's constant?
1 second. I'll share it again. Yeah. So value of Rydberg's constant is 1.097 into 10 to the power 7 per meter. Okay. Actually, one more thing also I can tell you. Right. So one more thing is this 1 by lambda is there, right? Okay, this 1 by lambda is what is called as some nu bar, that's a unit, and that nu bar is called wave number. Okay, so wave number is nothing but the reciprocal of the wavelength. Okay, and wave number is represented by mu, and you put a bar on the top of it. Okay, so 1 by lambda is equal to mu bar. Mu bar is nothing but the wave number. So I can even write this as mu bar is equal to RH into Z squared into 1 by Ni squared minus 1 by N squared. Okay, right? So remember this also. Basically, you learn two things. Frequency is equal to C by lambda, and mu bar is equal to 1 by lambda. These two things is what you have learned today. Okay, yeah, this is it. I want to stop here. Okay. Anybody has any questions? I hope everything is fine, right? So fine, guys. Thank you so much. We'll meet again tomorrow. Right? Till then, thank you. Bye-bye.
Thank you, sir.
Thank you, sir.
Okay, sir.
Yeah.